everyone, and welcome back to Easy Taleem. Today is actually a special day. Not because we are studying integration, but because after today's lecture, you will have completed the entire 9709/12 Cambridge AS Pure Mathematics 1 syllabus. Think about how far we have come. We started with functions, right? You remember it. Then we did coordinate geometry. Then we did series, and of course there was quadratics in here, and under series we had APGP and binomial expansion as well. And then we moved on to differentiation, and now finally we will be concluding the second part of calculus, that is integration. We already did the first part of it in our last lesson on Thursday, and today on Saturday we will be concluding the entire integration. And every one of those chapters wasn't designed to exist in isolation. Cambridge has quietly been building one idea after another, and today they all meet. Last lecture, we learned something beautiful. Suppose dy by dx is equal to 6x squared. Integration allowed us to rebuild the original function y, right? We saw that, but notice something. Our first and our final answer always looked like y equals to 2x squared, 2x cubed plus c, which is the arbitrary constant of integration, a whole family of curves, right? One on top of the other, varying with the value of c that it assumes, right? So this is not one answer, this is infinitely many. Today, everything changes. Today, instead of asking what was the original function, Cambridge starts asking what is the exact numerical value between these 2 points, right? And that is definite integration with limits. Definite integration. So far, we were doing indefinite integration when we were trying to rebuild the original function. Okay, so now, okay, now let's imagine something. Suppose someone asks you, "What is your height?" Right now, you may answer, "I'm somewhere between 5 feet and 7 feet." Technically, you are not wrong if you are indeed between 5 and 7 feet tall. But you haven't really answered the question precisely. Now imagine they ask, what exactly is your height? Now you give one number. You don't say that I'm between 5 and 7 feet and 7 feet. Now they're asking you, demanding you to give you the exact height. So you may say that, okay, I am, I don't know, 6 feet 1 inch, right? Done. Notice the difference. Last lecture, integration gave us a family, right? And today, we want one exact precise answer, and that is why definite integration exists. Okay? All right. Now, indefinite integration leads to functions. Indefinite integration, it leads to function. And definite integration, it leads to a number, okay, a numerical value. Now this is the difference. This is one of the biggest conceptual shifts in all of P1. Now if I write down that there is a function f of x and you have to integrate it from the limit x is equal to a to x is equal to b, and you have to integrate it with respect to x. Now in the last lecture, our integral looked like something without these two additional numbers a and b. It just looked like this. You integrated it, you got another function, and you would put a plus c here, right? There were no limits. We call them the limits, okay? Now today something has appeared, the two numbers. What are they? So we call this the lower limit of the function, and this is the upper limit. Simple names, but an incredibly powerful idea. We're no longer looking for every possible function. We're asking what happens only between these two values of x. Now, let's give you a real life analogy. Imagine driving from Karachi to Lahore, between two cities, right? Now, indefinite integration asks, tell me every possible journey anyone could ever make. So you can go to Lahore from Karachi through this route. You could go from this route, you could go directly, you could take a longer route, right? Now, definite integration asks, I only care about the shortest distance between Karachi and Lahore, so you are going to give them this one answer, and you're going to give them the precise value of the distance between Karachi and Lahore, and that's the shortest distance, right? Or they may ask you to find to give you the distance between this route, the exact distance on this route. Let's say this is M5. I don't know. Let's give this route a name, M5, right? Now this is one exact interval and one exact answer, right? Now why does this plus c disappear when you are doing, so plus c disappears when you are doing definite integration, okay, which means when you are applying the limits a and b to a function which is getting integrated with respect to the variable it is a function of. Now, so you may ask me that why don't we write a plus c anymore? Let's answer properly. Suppose when you integrate fx with respect to x between a and b interval, so you get an answer of fx is equal to, this leads to fx is equal to x cube plus c. Now if you have to evaluate between a and b, so that is going to become f of b minus f of a. Now f of b is going to become b cube plus c, and f of a is going to become a cube plus c. Can you now see that this simply becomes b cube minus a cube plus c minus c, and this gets cancelled, so we are just left with a numerical value that we have, right? So what happens here? The constants cancel every single time, so Cambridge doesn't ignore plus c, or the math or the calculus doesn't ignore it. It simply disappears naturally because you're subtracting one value of the same function from another, right? That is why definite integrals produce a single numerical answer rather than a family of curves, okay? Now the golden rule is, and you will write it down, that whenever we are integrating a function with respect to x between a and b limits, that the answer is going to be f of b minus f of a, where this capital F is the integrated function without the arbitrary constant of integration, and then you plug in the values b and a, and I'm going to do an example in order to make it much clearer, okay? So don't think that we are just going to shoot in the dark. So now, if there is one formula from today's lecture that you'll use repeatedly in Cambridge exams, this is it. But don't memorize it, understand it. Now, usually students memorize upper minus lower. There is nothing wrong, right? But almost nobody asks that why do we do upper minus lower, right? Let's prove it. Suppose you have to integrate 2x between 1 and 3, and you have to integrate it with respect to x. So the answer is going to become x squared upon 2 times 2, and the limit is from 1 to 3. So now this becomes x squared from 3 to 1. So this becomes 3 cube is 27 and 1 cube is 1. So the answer is going to be 26, right? Now, oh, sorry, this was x squared, right? So this becomes 8 minus 1, right? So sorry, 3 square is 9, 9 minus 1 square, so the answer is 8, my bad. Okay, now, so the difference is 8. Now what if I accidentally did lower minus upper? So what if I put this here and I put this here and I did 1 minus 9, I would get a minus 8. Now the definite integral shows the area under the curve, between the curve and the horizontal axis, right? So can this area ever be negative? Right? It can't be. So mathematics naturally forces us to evaluate upper minus lower. Now if I give you to evaluate x squared between 1 and 3, and you have to integrate it with respect to x, so that's going to become 1 cube x cube between 3 and 1, so that's going to become 27 over 3 is 9 minus 1 over 3, and that's going to be 26 over 3 squared units, because that's the area, right? Now, but don't rush. Most mistakes happen during substitution when you substitute the values of the limits, right? Make sure that you're always doing upper minus lower. You first plug in this value in the integrated function, and then you plug in the other value. Let me do it one more time. Let's do another example actually. So if you have to evaluate 3x squared plus 4 integrated with respect to x between 0 and 2, so this becomes x cube, 3x cube over 3, so this becomes x cube, and plus 4x, and you have to put the limits between 2 and 0, so this becomes 8 plus 8 minus, then you put 0, 0 plus 0, so we can just let it be. So the answer is going to be 16 squared units, right? Now Notice something, we never integrated directly between 0 and 2. We first found the antiderivative, only then did we substitute, right? And this is exactly the sequence that you will always follow. Now I want you guys to do another integral. Let's change the color. 6x with respect to x between 2 and 5, right? A common mistake is that students substitute first. You're going to put 5 here and then 2 here and then try, and then you are going to ponder that why is whatever is happening, why is happening with you. It is because you are substituting it first. You have to find the antiderivative and then you have to do the substitution. Okay, so this is the first step, this is the second step. So that's going to become 3x squared, and then you apply the limit 5 and 2. So when you apply 5, so this becomes 75, and when you apply 2 and you subtract it, this becomes 18. So 75 minus 18 is going to become 57, right? And that's going to be the answer. This mistake appears surprisingly often in Cambridge scripts because students confuse differentiation rules with evaluation. Now I want you to pause. Everything we have learned over the last month comes together here. Functions gave us equations, right? Now see, so functions, they gave us equations, and coordinate geometry, it gave us curves, right? Differentiation, it gave us gradients, right? And integration, it rebuild the curve, right? Rebuild the curve. I will write it down. Rebuild the curve. Now, definite integration extracts exact numerical information from that curve, right? Definite integration, it extracts the numerical value from that curve. Nothing you have studied has been wasted. Every chapter has quietly prepared you for this one. Now, imagine you're the examiner. Would you rather ask, can this student memorize a formula, or can this student understand why the formula works, right? So think from the examiner's perspective. Cambridge almost always chooses the second. That's why students who understand concepts consistently outperform students who simply collect formulas. Now, so far we have learned how to calculate a definite integral. But here's the real question. What does that number actually represent? I just mentioned to you that it's the area, but is it just another answer, or does it have a physical meaning? In the next part that I'm going to embark upon real quick, you'll discover why definite integration became one of the most important ideas in math, engineering, economics, and physics. We'll use it to calculate something that you cannot calculate using ordinary geometry alone, the exact area enclosed by a curve. So what I'm trying to say is that what if you have, okay, so let's say that you have a curve. Let's say this is y is equal to 4, and I want you to find out the area under it between the x-axis and this curve y is equal to 4, and I want you to find out the area between 5 and 7. I mean, that's pretty straightforward. You are going to find the base, that is 2. You are going to find the height, that is 4. So 2 times 4 is 8. That's pretty straightforward. What if you have another line going like this and you want to find out this, right? Let's say this line is this line is half x plus 2, right? Now they want you to find out this between 5 and 11. So that's pretty easy. You can see that this is a trapezium. So you can find out this function value. So 5 upon 2 plus 2 is nothing but 9 upon 2. And at 11 upon 2 plus 2 is going to be 15 upon 2, right? So very easy. So trapezium rule dictates, so half into height is going to be this, into sum of parallel sides. 15 upon 2 plus 9 upon 2 is 12. So that's going to be 3 times 12 is 36. So 36 squared units, right? Fairly easy. Now tell me something. What if I give you a parabola and I want you to find out the exact area between this point and this point? How can you find out this area? This is not a circle, not an ellipse, it's a parabola, right? Now you cannot find this area under a curve and area between curves. Let's say there's another parabola and I'm asking you to find out the area between these two parabolas. How are you going to do it? You cannot, right? So I deliberately avoided answering this one question in the at the start of this, but now we are going to do that, right? Now let's try to pick it up from a very basic example. Let's say this is my x-axis. Let's draw a curve. Let's say a curve goes like this: y is equal to f of x, right? Now, if I have to find out the area between x is equal to 1 and x is equal to, let's say, 4, right? If I have to find out the area between these two limits, let me shade it as well so that we can visualize it. If I have to find out this area, right, how are you going to do it? You cannot. There is no method that you have studied so far that is going to achieve it for you, right? So you may turn it into a rectangle, but can you see that this is going to over record it, right? So we cannot do this. We just found out. What if you turn it into a trapezium? Okay, that's much closer, but again, you are over recording it, right? What if you turn it into, I don't know, a rectangle and a triangle, right? What if you do it? I mean, you still are closer because that's just another way of looking at the trapezium formula. So you could split it, but this isn't a rectangle, it's not a triangle, it's not a trapezium, it's not even a shape you've seen before, right? So how do you calculate its area? That's exactly why integration was invented, and we are delving into that. So imagine this curved region is made of infinitely many triangles, and let's do it. So let's say, okay, let's say this is made up of these tiny strips, and these are very, very tiny strips. Of course, I cannot spend a lot of time in trying to make perfectly vertical lines and showing it to you, but yeah, you can imagine, right? So these are tiny rectangles. This is one tiny rectangle, this is another tiny rectangle, then this, then this, then this, then this. And if I make them very, very fine thin strips, then this over recording that's happening, we are going to minimize that, right? So what is the area of any one strip? If I say that the width of any of the strips is nothing but d of x, right? Dx, sorry, not d of x, it's dx, precisely dx. So this width is dx. So at any particular value, this is going to produce the function value at every particular value of the variable, of the independent variable x, right? So every strip has an area f of x times d of x, right? And how many of them are there? They are from here to here, right? So if one tiny strip has this area, what happens if I add infinitely many of them together in this interval between 1 and 4? So this whole area is you're going to obtain this entire blue shaded whole area, exactly. And so we can rewrite it as, you do the sum or you do the integration between 1 and 4, and generally you are going to write a formula, or you are going to write a notation that in order to find this area, you have to integrate it between the lower limit and the upper limit. Now I'm going to connect it with something that we did last time. So this isn't just another formula, it literally means that you add the areas of infinitely many tiny triangles. Now remember this integration symbol that we did last time? It came from the letter S, an elongated S actually, and this S meant sum. So today you finally understand why integration is simply adding infinitely many tiny pieces together. That is far more beautiful than memorizing that area equals to integral, right? Don't just memorize it. Now you understand that y is area equal to the integral, right? Definite integral. Now, if I ask you to find the area enclosed by y is equal to x squared, the x-axis, and the line x is equal to 1 and x is equal to 3. Now, first I want you guys to visualize it. Now, what does y equals to x squared look like? It looks like a parabola that goes like this. I've not done a very good job with drawing this parabola, but yeah, it does look something of this sort, right? So we are trying to find out between this curve. Let me put the, oh my god, wait. Wow. So perhaps it wants me to draw it nicely. Okay, so let me do it. So x squared looks something like this. Okay, so this is y equals to x squared. Now y, so this is x is equal to 1, this is x is equal to 3. The function values are going to be 9 and 1, and it wants you to find out this area between this curve and the horizontal axis. So this is the curve. Let me do it with blue. This is the x-axis. Let me do it with yellow. and these are the two lines which I did with red, right? So basically we are interested, or we are required to find out this area right in the middle. So I can now, let me draw the exact line. So 1 1, the function value is not needed here actually, but let me just do it regardless. Okay, so this is 9 and this is, sorry, 3. So we are interested in this formula. So how do we do it? So we integrated between 1 and 3, we put x squared, and we integrated with respect to x, right? So this becomes 1 3, 1/3 of x cubed. We put the limit 3 and 1, and the answer is going to become 26 upon 3, like we saw earlier, right? So notice something, that the exact same calculation from part 1, but now we know what the answer represents. It represents the area under the curve and above the x-axis and between the limits 1 and 3. It isn't just a number, it's an area. Okay, now what's the biggest Cambridge trap here? Let's draw two curves. So there is this one curve, y equals to f of x, and then there is this another curve, y equals to g of x. Okay, now, so the above curve between these two limits, let's say this is a and this is b. So the brown curve is above the green curve, right? If there are two curves, which one do we integrate? Now, a lot of you will usually become confused but I want you to give it, and basically the requirement of this question is that you have to find out this area between these two curves, right? Now, this is a fairly simple idea. So if I were to look at it, what I'm going to do is, basically I'm going to find out all of this area. So I'm going to integrate g of x with respect to x between a and b, and then from here I'm going to subtract this excuse me, this other area between the lower curve, right? And that's going to make it, between a and b, I'm going to subtract this area of f of x with respect to x. And now I can rewrite it as, the limits are same, dx is same, so I can just do g of x minus f of x. And this is what exactly we did at the start, that if you have 2x plus 3 dx, so this can be written as 2x dx plus 3 dx, right? So I just reversed the process and I encapsulated it between one integral, right? So this is upper, this is lower. So always do that. Top curve minus bottom curve. Do not do left minus right. Do not do first minus second. Always top minus bottom. Top minus bottom. Okay. Now, why do we do top minus bottom? I just proved it here that this is exactly how you do it. So for any two figures, if you had to find out between the area, for example, you are, okay. Excuse me, wait a second. Okay. So let's try to prove it. Suppose your upper curve is y is equal to 7, which is a straight line, and your lower curve is y is equal to 2. And your lower curve is y is equal to 2. And you have to find out the area between them, between the limits 1 and 3. So how are you going to do it? You're first going to find out this area, and then you are going to find out this other area, right? So first you found out the area of the top one, and then you found out the area of the bottom one, and hence you found out this area, right? So nothing magical happened. It's simply the height of every rectangle, right? Now, if I ask you to find the area enclosed between y is equal to x squared and y is equal to x plus 2. So y is equal to x squared is this, and y is equal to x plus 2 is this, right? Y is equal to x plus 2, and this is y is equal to x squared. And if you have to find out this area between these two curves, so how are you going to do it? First, you will do top minus bottom. So top is x plus 2, bottom is x squared, and now you have to integrate it. But you just realized that, okay, I don't know these limits, so I have to find out these values as well. What is b and what is a? So you are going to solve them simultaneously. So this becomes x squared minus x minus 2 equals to 0. So x squared minus 2x plus x minus 2 equals to 0. So x minus 2 and x plus 1 equals to 0. Therefore, x is equal to 2 and x is equal to negative 1. So a is negative 1, b is 2. So you put these limits and bam, there you have your answer. Let's do it very quickly. So this becomes this becomes x squared over 2, this becomes plus 2x, and this becomes minus 1/3 of x cubed, and then you apply the limits 2 and minus 1. So when you apply 2, you get 4 upon 2 is 2 plus 4 minus 2 cube upon 3, 8 upon 3, right? Sorry, minus 8 upon 3. And then you apply the limit minus 1. So minus 1 makes it minus, oh sorry, 1/2. This makes it minus 2, and this makes it minus 1, minus 1 over, so plus 1 over 3. So this becomes so 6 and minus 8 over 3, and minus 1 over 3 is minus 9 over 3, and then we have a plus 2, and then we have a minus half. So 6 minus 9 over 3 is 6 minus 3 plus 2 and minus half. So 3 plus 2, 5, 5 minus half is 9 over 2 square units. All right. So it is as simple as that. Now, so this is one of the most repeated structures in P1. You have to integrate carefully, and then you have to evaluate, obtain final answer. So make sure that you are working every algebraic step slowly in your answer scripts. Okay, and I want you guys to pause the video and do it again in your notebook, so that the concept is cemented in your heads. Now suppose the curves cross twice. One graph is above here. Now let's say your curve is, so there is a cubic curve and then another curve, right? What if you're being asked to find out these two areas, right? Let's say this curve is y is equal to f of x, and this curve is y is equal to g of x. So now, in order to find out this area, you cannot just take these two limits and just do upper minus lower, because in this interval, fx is upper, no, gx is upper, and then in the second interval, f of x is upper, right? So you have to basically break it into three limits. So you have to solve it simultaneously and find out a, b, and c, and then you have to do, so you have to first integrate between a and b, this first region, and you will do g of x minus f of x, because g of x is above, right? So this becomes g of x minus f of x dx. So that's first, and then you are going to add to it between b and c, the second region, and here f of x is above, so you are going to do up top minus bottom, and this is how you are going to evaluate it. So we did not use just one integral, we split the region every time the upper graph changes, and so we start another integral. Now this isn't difficult mathematics, it's just careful thinking, right? It's just logic. Now notice how many chapters we have used. We have used functions, we have used coordinate geometry, we have used algebra in order to find intersections, to solve equations. We have used differentiation to understand curves. We are using integration to calculate area. We are using definite integral, right? So functions was used to identify equations. Coordinate geometry was to find intersections. Algebra was used to solve equations. Differentiation was used to understand curves, and integration is now being used to calculate the area. Cambridge never really examined separate chapters. It has always examined your ability to connect them, right? So this is what you observe over the years when you're trying to make sense out of all the questions they ask you in every exam, every time, in all the variants and all the sessions across the years. Okay, now if now why should anyone care about area under a curve, right? But engineers use it, of course. When you're building a car, for example, everything matters. When you're optimizing, how much weight must it be, how much paint would it require when you're producing Toyotas in bulk, right? So physicists use it as well, because they need a lot of precision. They cannot just create triangles and then do over recording, right? They need precision, right? In there, biologists use it, Economists use it. If the graph represents speed, area gives distance. If it represents power, area gives energy. You know it. If it represents rate of production, area gives total production. Integration transforms rates into totals. That's why it's everywhere. Now, Cambridge doesn't really care whether you can shade a graph. It cares whether you recognize. And what do you recognize? Whether you can recognize which function is above, where they intersect, that is going to form the limits or the split limits, what interval to use. The integration itself is often the easiest part. Choosing the correct integral is where top students separate themselves. Now, so far we have answered two questions. How do we calculate definite integral, and how do we use it to calculate areas, right? So this is 1, this is B, this is A. Now we are going to do something even more remarkable. We are going to take a two-dimensional shape, spin it around an axis. So this is a two-dimensional shape, but what if you spin it around the x-axis, right? And calculate the volume of the three-dimensional object that it creates. So for example, if I give you y is equal to x, if you rotate it around the x-axis, you are going to form a cone, right? Now, let's welcome you to one of the most elegant applications of integration. Okay. So we are half an hour into the lecture. So far, we've used integration to calculate areas, but now let me show you something that, in my opinion, is one of the most elegant applications of integration. And so what happens if that area starts spinning, right? So this was the area, but now it starts spinning. So this was the area, and now it's spinning. Okay, wait a second. Okay, so this is what happens when your gadgets are interconnected. I was I was getting distracted on my tab. Okay, so what if this area starts spinning, right? So imagine that you have this triangle, but now this starts to spin like this, right? So if it starts to spin 360 degrees vertically, or if horizontally, it's going to start creating a three-dimensional solid. And integration tells us exactly how much space that solid occupies. Okay. Now, suppose I draw the curve y equals to x squared. Now, between x is equal to 0 and x is equal to 2. So let's say that the curve is like this. Between x is equal to 0 and x is equal to 2. Right? Now, it's just a flat region, right? In 2D, it's just a flat region. Now imagine grabbing the x-axis and spinning the entire shaded region around it. So we anchor it and we start spinning this. Start to spin this shaded area around it. So we started to spin. So now imagine. So it no longer remains flat. It becomes a solid, right? Something I cannot really. So if you look at it from this angle, so this is going to look something like this. Okay, now so it becomes a real object, almost like a bowl. Now where does so in the volume formula, a lot of the students ask that why do you put a pi here in the function? And the question is, so this is the way that you do it. So you're going to put the limit 0 and 2, you're going to square the function, and then you integrate it, and then you put a pi. And students are going to ask that where does this pi come from? Now look here. So if this is the curve, or if I make a straight line, now if we are spinning it, so what is really happening? We are getting a lot of disks, right? So you can imagine a disk. Okay, you can imagine a disk running from here to here, here to here, then here to here, right? What is the radius of this disk? The radius of this disk is going to be the function value, right? And what is the area of this disk? The area is going to be pi r. R is f of x, and r is a squared. So pi r squared, right? And how many disks are these? These are disks from 0 to or A to B, right? So you integrate between A and B, and along the many disks, right? So therefore we get f of x whole squared integrated between the interval, right? And this gives you the volume, and then you multiply it by pi, right? So this is how it happens. Now, so this is one disk. It is tiny. Thousands of disks, it forms a complete solid, and therefore this is the area. So f of x, sometimes you can also see y squared, which is one and the same thing, right? This is one of the most elegant formulas in P1. Now, let's give you an example. So if I want you to find the volume generated when y is equal to x squared over the interval x is equal to 0 to 2, which we just drew above. So what is going to be the volume of this when it is rotated about the x-axis? Now, so first you are going to square it. So x squared becomes, so x squared, you square it, you put a dx, you put the limit 0, 2, and you put a pi in order to get the volume. Now this becomes pi, and this is 1 over 5x5, and then you put the limits from 0 to 2, so this becomes 32 over 5 minus 0 over 5, that is just 0. So this is the answer, 32 pi over 5 cube, units cubed, or whatever, right? Units cubed, because this is volume. Okay, now what's the biggest mistake? Students often write pi integral y dx and the limits whatever, right? This is wrong, because what is the area of a circle? It's not pi r, it's pi r squared, right? Y is the radius of this disk, therefore you have to square it, so the function must always be squared. Now what about when the region is not touching the axis, right? This is where Cambridge becomes interesting. Now suppose y is equal to 9 minus x squared. Y is equal to 9 minus x squared. So you draw it like this. So this is 9 and 9, and y is equal to 5. There is another line, y is equal to 5, right? Now you have to rotate the region about the x-axis, right? Now there is a hole in the middle, right? You have to rotate this region about the x-axis. So you are going to produce, so this is going to come, so you are going to find out this cylinder which is going to be missing, right, from the middle, right? So there is a hole in the middle. Now this is not one solid disk, it's like a washer or a donut sort of a thing, right? So the outer radius is going to be 9 minus x squared, right? So this is the radius, and the inner radius is going to be this 5, right? So you have to do this. So this radius minus this radius, and then you put the limits, whatever the limits are, from a to b. Okay, and then you have to integrate it in order to obtain the volume. Or you could just obtain the volume of this entire thing, right, of this entire thing, and then you subtract the volume of the cylinder, the height of which is going to be this much, the height of which is going to be this much, and the radius of which is going to be 5, right? You either way you're going to get the same answer, right? So now notice what happened. Outer circle minus inner circle, exactly the same logic as area between curves, top minus bottom. Now it becomes outer squared minus inner squared. This is precisely the type of situation Cambridge mentions in the syllabus notes as well. If you go in and I would recommend that you guys must all go and download the PDF of the syllabus and make sure that you have gone through it thoroughly. Now, when you see volume of revolution, don't rush into integration. Ask yourself 4 questions, and I have written it down, and I'm going to tell this to you. What axis am I rotating it about? Whether this is about the x-axis or whether this is about the y-axis, right? Now, what is my radius going to be? Right? Radius is always going to be the function value of the disk. Is there an inner radius? Is there an inner radius, right? This is a must ask question. And am I using pi r squared, or am I using pi r squared minus r squared? Outer minus inner, right? If you answer these before you write a single equation, the math becomes straightforward. Now, there are quite a few Cambridge traps here. Students lose marks because they forget to square the radius, they use the wrong radius, they forget the pi, they use top minus bottom instead of outer minus inner. So you have to integrate correctly, but evaluate the limits. So you will. So a lot of students, they are able to integrate correctly, but they evaluate the limits incorrectly. Now, so you may wonder that we spoke about y-axis as well. So what about if Cambridge asks you to integrate y is equal to 2 minus x, let's say this is the line, about the y-axis between 0 and 3 on this interval, right? Now 2 minus x looks something like this, right? Now instead of doing this, they ask you to do, and let's say, so at 3, or not 3, at 2, so that we get it easier. Now this is the cone that you're forming, right? And actually, so when they say 0 and 2, you have to find corresponding, so this is on x, right? You have to find the corresponding range on y. So when x is equal to 0, y is equal to 2, and when x is equal to 2, y is equal to 0. So you have to rotate it around here, but you have to convert it into x as a function of y. So this becomes 2 minus y. So function of y is 2 minus y. So sorry, 2 minus y. So now you're going to integrate 2 minus y whole squared, because now this 2 minus y is the radius, and you put a pi here and you do dy, and you put the limit 0 to 2, and this is going to give you the volume here, right? So this is how you're going to do it.